Welcome to this video. In this video, we will solve exercise 41, 42 and 43 of the chapter 2 from book Contemporary Abstract Algebra 10th edition by Joseph A. Gallian. We start with the question 41 and the statement is let R be any fixed rotation and F be any fixed reflection in the dihedral group, then prove that r to the power k f r k is equal to f. So here binary operation is composition of function. We know that product of here product mean composition of function of reflection and rotation in dn is reflection. Okay. And the product of two rotations in dn is again rotation. And also we know that the composition or product of two reflections is also a rotation, but we do not require this result here. So we start let f belongs to dn is a reflection is fixed and r which is rotation belongs to dn is fixed. Okay, let we consider rk is also rotation for any k belongs to set of integers because it is actually composition of R with itself k times, and we have seen that the product of rotations is again rotation. So Rk is also rotation. Now we know that F is reflection and this Rk is rotation. So this means Frk is reflection. This means the scale of this reflection is identity element. We know that every reflection has order 2, means whenever we will take care of any reflection we will get the identity. This can be written as frk frk is equal to r naught. Okay, now if we pre-multiply both sides with f inverse, we get f inverse r naught. This will be identity. So we will get rk frk is equal to f and f inverse, sorry. But we know that for every reflection, f inverse is f itself. So this implies that rk f rk is equal to f, and that is what we want to prove. Okay, we move to the next question, question number 42, and the statement is let r be any fixed rotation and f any fixed reflection in a dihedral group. Prove that f RKF is equal to R to raise power minus K. And why does this imply that Dn dihedral group is non-abelian? Okay, we know that FRK whole square can be written as FRK FRK, and that is of course identity because FRK is a reflection. So this implies if we post multiply or multiply from the right side of this equation with R to raise power minus K, we get this will be identity, and FRK F is equal to R to raise power minus K. So this is what we want to show. Now the remaining part is, why does this implies that Dn is non-abelian? This is remaining. Okay, we assume on contrary or suppose that Dn is abelian for n greater or equal to 3. Okay, now if it is abelian, then f rotation with angle 360 over n into f will be equal to rotation with angle 360 over n, because if it is abelian, then this can be written as, actually we prove again, consider this, and because we have assumed that the dihedral group is abelian, so these two can be permuted, r 360 over n, and that will be f square r 360 over n, and we know that f square is identity, so r 360 over n, f r 360 n f. Okay, and we know that this means, it means r 360 over n inverse, if we take, it will be f r 360 of n f inverse, and that will be f inverse r 360 over n inverse and f inverse. Okay, and this can be written as r 360 over n into f inverse, and this f is inverse of itself. So also we know that the product of rotation and reflection is again reflection, so its inverse is itself, and here we get f square, which is also identity. So if we see, we get actually the contradiction, because this is rotation and it is inverse of itself every time, which is not possible. So this is contradiction, and this contradiction appears because we assume that Dn is abelian group. So Dn is non-abelian. Okay, we move to the next question, question 43, and the statement is let R be some rotation in dn and f some reflection in dn. Now express R6 FR FR minus 3 FRF in the form of RK and express FR4 FR5 FR square in the form of RKF. We start the solution. Okay. Since FR is reflection, so FR square is the identity element, and that can be written as FR into FR is equal to R naught, and we post multiply with the inverse of this R, and we get FRF, because this will be identity, is equal to R inverse. Okay, and now we pre-multiply both sides with F inverse. We get, okay, F inverse F RF is equal to F inverse R inverse, and that will be identity. So this will be RF is equal to, and this F inverse will be F itself. So we get that RF is equal to FR inverse, and similarly we can get that FR is equal to R inverse F. So these two results we have proved actually to prove the remaining part of this theorem or this question. Now we consider, okay, R6 FR FR minus 3 FR F. We will use these two results in proving this consideration, okay, that can be written as FR minus 6. We have changed this to this by using this result, and then R F R minus 3 FR and F, and that will be F R minus 5 FR minus 3 FR and F. Okay, now again we will use this result. It will be R5 R minus 3 and this one, and this will be identity. So, and we combine this, we will get R square FR and F. Okay, this FR will be equal to R inverse F. So this will be R square R inverse F and F, and this F square will be identity, and we will get only R. So R6 FR FR minus 3 FR and F, and this is equal to R, and that is what we want to prove. Okay, we now move to the second result. Okay, I write those derivations here because we have to use these for the proof of second part. Now consider fr4, fr5, fr square is equal to, this will become, due to this result, it will become r raised power minus 4 fr5 fr square. These product of f will become identity, and we will get f raised power minus 4, sorry, r raised power minus 4 into r raised power 5 f r square, and that will be r f r square. And now we again use this result, that f r will be r inverse f, and that will be r minus 2 f, and that is equal to r raised power minus 1 f, and that is what we want to show. So that's all about today's video. Please like the video and subscribe the channel.